It's a night unlike any other, a vast, unbroken expanse of darkness, interrupted only by the cold, distant glow of ancient stars. The blackness of space stretches in all directions, infinite and unyielding. Here, in this silent abyss, time itself seems to lose meaning. You are an astronaut, floating freely, untethered from your spacecraft. The Earth, a brilliant blue and white marble, spins below you. Yet, something feels off. You glance at your wristwatch, expecting the familiar tick of seconds marching forward. But the hands seem sluggish, reluctant to move. You blink, shake your head, and look again. Nothing has changed. Then, a flicker of movement catches your eye. The distant stars, which should be constant and unwavering, appear to twinkle at irregular intervals. Their light seems stretched, distorted, as if reality itself is bending around you. On board the spacecraft, your crewmates continue their routine, checking instruments, conversing, floating effortlessly in microgravity. Their movements appear normal. Time inside the ship flows as expected. But out here, where you drift alone in the void, time is different. You take a deep breath, trying to calm yourself. You've studied this phenomenon before, time dilation, a prediction of Einstein's theories. But now, experiencing it firsthand, you feel something deeper, something unsettling. A question echoes in your mind. What is time? From the moment we are born, we live under the rule of time. It dictates our lives, marking the passage of childhood, adulthood, and old age. It determines when we wake, when we work, when we rest. We measure it with clocks, count it in years, and fear its relentless march forward. But what if time isn't real? What if everything we experience, past, present, and future, exists simultaneously? What if time doesn't flow at all? To us, time seems like a river, moving in one direction from past to future. But some of the greatest minds in history have questioned whether this perception is real or merely an illusion created by our consciousness. If we could step outside the universe and look at time from a higher dimension, would we see all of history laid out like a vast, unchanging landscape? The implications are profound. If time is an illusion, then free will might also be an illusion. Every decision we make, every action we take, might already be determined, like a film reel where the ending is already written, but we can only watch it unfold moment by moment. The nature of time has puzzled philosophers and scientists for centuries. The ancient Greek philosopher Parmenides argued that change was impossible and that all of reality existed as one static, unchanging whole. To him, time was an illusion created by our perception. Heraclitus, on the other hand, believed the opposite, that the universe was in constant flux and that time was the very essence of change. These early debates set the stage for thousands of years of inquiry into the nature of time. Plato saw time as a moving image of eternity, a mere shadow of a deeper reality that existed beyond human perception. Aristotle disagreed, insisting that time was not an independent entity, but simply a measure of change. These contrasting views shaped Western philosophy's approach to time for centuries. With the rise of modern science, time became something measurable, something that could be studied and quantified. Isaac Newton treated time as an absolute universal constant, flowing at the same rate for all observers, independent of space and matter. To Newton, time was like a giant cosmic clock ticking away in the background, unaffected by the events occurring within the universe. Then, in the early 20th century, everything changed. Albert Einstein's theory of relativity shattered Newton's vision of time. Time, Einstein showed, was not absolute. It was flexible, elastic, woven together with space itself into a four-dimensional fabric called space-time. The faster an object moved, the slower time passed for it. Gravity could stretch and warp time, making it pass at different rates for different observers. This was more than just theory. Einstein's predictions were later confirmed by precise experiments. Atomic clocks placed on fast-moving jets or high-altitude satellites ticked at different speeds compared to identical clocks on Earth. The implications were staggering. If time could be stretched and warped, what did that mean for our everyday experience of reality? Could time, as we understand it, even be real? One of the most radical consequences of relativity was the idea of the block universe. According to this view, all of time, past, present, and future, exists simultaneously. The universe is not a film reel playing from beginning to end, but rather a completed film with every frame already in place. What we perceive as the flow of time is merely our consciousness moving along a fixed path through this unchanging four-dimensional structure. If the block universe is correct, then the future already exists, just as much as the past does. The moment you were born, the moment you are experiencing right now, and the moment of your death are all equally real, frozen in the fabric of space-time. This idea is difficult to grasp because it contradicts our most basic intuitions. We feel time moving forward, slipping through our fingers like sand. But that might be nothing more than an illusion, a trick of our perception. If this is true, then it raises unsettling questions about free will. If the future is already written, then are we truly making choices? Or are we simply following a predetermined script, believing ourselves to be in control when in reality, every action we take is already fixed in the structure of space-time? Some scientists and philosophers argue that consciousness itself may be responsible for our perception of time. Our brains process information in a way that creates the sensation of a flowing present, but in reality, all moments exist equally. It is our awareness that moves through them, like the beam of a flashlight illuminating different parts of a vast landscape. But if time is an illusion, what does that mean for the universe itself? Could the cosmos exist in a timeless state, with all events happening at once? Some physicists suggest that time is not a fundamental property of the universe at all, but rather an emergent phenomenon, something that arises from deeper laws of physics that we do not yet fully understand. Quantum mechanics, the strange and counterintuitive theory that governs the behavior of particles on the smallest scales, seems to hint at this possibility. In the quantum world, particles do not have definite positions or states until they are observed. Some interpretations suggest that time itself is an emergent property of quantum interactions, not an underlying feature of reality. If time is an illusion, then what about the future? Is it truly unchangeable, or is there some way to rewrite the script? Some theories suggest that while the block universe may exist, there could still be room for change, perhaps through quantum uncertainty or parallel realities branching out from every decision we make. Standing here, floating in the vast emptiness of space, you begin to wonder, are you truly experiencing this moment, or has it already happened? Could there be another version of you in another timeline making a different choice? Or are all possibilities already set in stone, waiting to be played out in the grand theater of the universe? As you continue to drift, the Earth below continues its silent, ceaseless rotation. The stars remain fixed in their distant places, their light traveling across the abyss, telling the story of a universe that may have no true beginning or end. Perhaps time is not something we move through. Perhaps time is something we are. The ancient Greeks were among the first to seriously contemplate the essence of time. To Parmenides, the idea of change itself was an illusion. He argued that the universe was a single, unchanging whole, and that our perception of time flowing was merely a trick of the senses. To Parmenides, the past, present, and future already existed, fixed and immutable, and what we experience as now was just our limited perspective on this eternal reality. His ideas stood in stark contrast to Heraclitus, who believed that change was the fundamental nature of existence. No man ever steps in the same river twice, he famously said, because both the man and the river are constantly changing. To Heraclitus, time was the very essence of reality, the driving force of all things, shaping the universe in an endless process of becoming. These two conflicting ideas set the stage for centuries of philosophical debate. Plato believed time was a mere moving image of eternity, a reflection of a deeper, timeless reality. Aristotle, however, took a more practical view, arguing that time was simply a measure of change. He saw it as something real, but only in relation to motion and events. It had no existence of its own beyond the physical world. For centuries, time was thought of as an absolute entity, something that existed independently of everything else. When Isaac Newton formulated his laws of motion and gravity in the 17th century, he imagined time as a universal clock ticking at a constant rate, independent of the universe. To Newton, time was like an invisible thread stretching across existence, providing a fixed backdrop against which all events unfolded. But then, everything changed. In the early 20th century, Albert Einstein shattered Newton's vision of time. His revolutionary theory of relativity showed that time was not an independent, absolute force. It was fluid, flexible, and deeply connected to space itself. Space and time, Einstein argued, were part of the same fabric, space-time. The consequences of this idea were profound. It meant that time could stretch and contract, depending on motion and gravity. The faster you move, the slower time passes for you. The stronger the gravitational field you are in, the more time slows down. Time was no longer a universal constant. It was relative, changing based on where you were and how you moved. This wasn't just theoretical speculation. Experiments have confirmed it repeatedly. Atomic clocks placed on high-speed jets tick more slowly than identical clocks on the ground. Astronauts aboard the International Space Station age slightly slower than people on Earth due to their high velocity. The GPS satellites orbiting our planet must adjust their timekeeping to account for both their speed and the weaker gravity they experience compared to clocks on Earth's surface. Without these corrections, GPS navigation would quickly become useless. But perhaps the most mind-bending implication of Einstein's work was the idea of the block universe. If time and space were woven together into a single fabric, then time was not something that flowed. It was already there. Every moment in history, from the birth of the universe to the farthest reaches of the future, coexists within this vast four-dimensional structure. In this view, the past is not gone, and the future is not something that has yet to arrive. All moments exist equally, like different locations on a map. What we experience as now is just a single point in this greater structure, one frame in a film reel that is already fully formed. But if the block universe is real, what does that mean for free will? If the future already exists just as much as the past, then our choices might not be choices at all, just the illusion of decision-making in a reality that is already set. Every action we take, every thought we have, could already be embedded within the fabric of space-time. This idea is unsettling, yet some physicists and philosophers argue it is the only logical conclusion. If time is truly another dimension, then the idea of changing the future is as meaningless as trying to change a particular coordinate in space. The future doesn't unfold, it simply is. But not everyone agrees with the block universe interpretation. Some physicists argue that time is an emergent property, something that arises from deeper laws of physics, rather than being a fundamental aspect of reality. In quantum mechanics, time behaves in strange and unpredictable ways. Particles can exist in multiple states at once, their futures undecided, until they are measured. Some interpretations suggest that reality itself does not have a single fixed timeline, but instead branches into countless possibilities. This idea leads to the concept of the growing block universe, a middle ground between eternalism and presentism. According to this view, the past and present exist, but the future does not yet. The universe is constantly expanding, with new moments being added as time progresses. The future is not predetermined, but unfolds dynamically, shaped by quantum uncertainty and the choices of conscious beings. This concept aligns more closely with our everyday experience of time. We feel the past as something fixed, something we can remember but not change. The future, however, remains uncertain, something we anticipate but do not yet see. The growing block universe suggests that the present is where reality is being created, moment by moment, as the universe continues to evolve. Yet, even this idea raises more questions than it answers. If time is truly something that is being created, then what determines how it unfolds? If the future is not fixed, then what guides the path it takes? And if quantum mechanics allows for multiple possibilities, does that mean there are multiple realities, alternate timelines, branching out with every decision we make? Some scientists believe that the answer to these questions may lie not in physics, but in consciousness itself. Our perception of time is deeply tied to the way our minds process information. We experience life as a sequence of moments, one following another, creating the illusion of a flowing present. But this experience may not reflect the true nature of time. It may be a feature of our consciousness, rather than a fundamental property of the universe. In this view, consciousness does not move through time. It simply exists at different points along the timeline. Just as we only experience one location at a time as we move through space, we only experience one moment at a time as we move through space-time. But all of those moments, the past, the present, and the future, are equally real, waiting to be observed. This idea is difficult to grasp because it contradicts everything we feel about time. But if relativity and quantum mechanics have taught us anything, it is that the universe is far stranger than we ever imagined. The flow of time may be nothing more than a trick of perception, a mental construct designed to make sense of a reality that is far more complex than our senses can comprehend. As you float in the silence of space, watching the Earth slowly turn below, you begin to wonder, is this moment happening now, or has it already happened? Could the future already be written, waiting for you to reach it? Or is it still being created, shaped by choices you have yet to make? Perhaps time is not something that moves forward. Perhaps it is not something that exists at all. Perhaps time is simply the way we experience a universe that is already complete, every moment laid out like the pages of a book, waiting, unchanging, eternal. A silent darkness stretches infinitely in every direction. If someone could step outside time and look at the universe as a whole, what would they see? Would they witness history frozen in place, with every event existing at once? Would they see the future, not as something unfolding, but as something already there? If the block universe is correct, then the past, present, and future are all equally real, permanently etched into the structure of reality. But if this is true, can we move freely through time the way we move through space? Can we visit the past or leap into the distant future? Science suggests that one of these journeys is possible, and it has already been observed. In 1971, physicists Joseph Hafele and Richard Keating conducted a simple yet profound experiment. They took highly precise atomic clocks and placed them on commercial airliners traveling around the world. When they compared these airborne clocks to identical ones that remained on the ground, they found something astonishing. The clocks on the moving planes ticked slower than those left behind. Time itself had passed differently for the travelers. This was time dilation, a direct consequence of Einstein's relativity. The faster you move, the slower time flows for you compared to someone at rest. This means that if a person were to travel at speeds approaching the speed of light, they could experience time at a dramatically slower rate than people left behind. A spaceship crew could embark on a journey through the cosmos, travel for what feels like a few years, and return to Earth to find that centuries had passed. This isn't just theoretical. Every day, cosmic rays, high-energy particles from space, slam into Earth's atmosphere and produce secondary particles called muons. These muons should decay in millions of a second, never surviving long enough to reach the ground. Yet, due to their extreme speeds, time slows down for them, and they live long enough to complete their journey. Time travel to the future is not just possible, it happens constantly. Every astronaut aboard the International Space Station is technically a time traveler, aging slightly slower than the people on Earth. But while traveling forward in time is allowed by physics, traveling backward is far more problematic. If time travel to the past were possible, it would create paradoxes that seem impossible to resolve. Consider the grandfather paradox. If you traveled back in time and prevented your grandparents from meeting, you would never be born. But if you were never born, how could you have traveled back in time to begin with? There's also the bootstrap paradox, where an object or piece of information appears to have no origin. Imagine you find an old physics textbook and use it to learn everything about time travel. You then build a time machine, travel back in time, and give the same book to your younger self. That younger version then grows up, uses the book to learn physics, and repeats the cycle. But where did the book originally come from? It seems to exist in an eternal loop without ever having been created. These paradoxes suggest that something fundamental about our understanding of time is incomplete. Physicists have proposed several ways the universe might avoid such contradictions. One idea is that nature enforces self-consistency, meaning any event that would lead to a paradox simply cannot happen. For example, if you traveled back in time and tried to change history, the universe would subtly prevent you from doing so. Your actions might be constrained in ways that always ensure events unfold as they already have. Perhaps you try to stop a historical event only to accidentally cause it instead. In this view, time travel may be possible, but only if it doesn't create logical contradictions. Another possibility is that the universe splits into multiple timelines whenever a change is made. According to the many worlds interpretation of quantum mechanics, every possible outcome of an event creates a new branch of reality. If this is true, then traveling to the past wouldn't alter your own timeline, but would instead create a new timeline in which events play out differently. This idea is often explored in science fiction, where travelers create alternate histories rather than changing their own past. But if this is the case, then true time travel, returning to your own past and changing it, might still be impossible. The laws of physics allow for the possibility of closed time-like curves, paths through space-time that loop back on themselves. In 1949, the physicist Kurt Gödel discovered a solution to Einstein's equations that described a rotating universe where time travel was theoretically possible. In such a universe, an object following a specific trajectory could eventually return to its own past. But there's a problem. The universe we live in does not appear to rotate in the way Gödel's model required. And even if closed time-like curves exist in some form, we would still need a means to access them, some kind of bridge through time. One of the most intriguing possibilities is the wormhole. A wormhole is a theoretical tunnel connecting 2 points in space-time, like a shortcut through the universe. If one end of a wormhole were placed near a massive gravitational field or moved at high speeds, time dilation could cause time to pass differently at each end. Entering the wormhole at one end could allow a traveler to emerge at the other end at an earlier point in time. This idea was popularized by physicist Kip Thorne, who suggested that an advanced civilization might be able to stabilize a wormhole using exotic forms of energy. But even if this were possible, building a time machine out of a wormhole presents immense challenges. The amount of energy required would be astronomical, and any attempt to manipulate time in this way could potentially trigger instabilities that destroy the wormhole before it could be used. Even if we could build a time machine, another question remains. Why haven't we met any time travelers? If time travel to the past is possible, where are the visitors from the future? Some argue that time machines might only work from the moment they are built onward, meaning no one could travel further back than the invention of the first working time machine. Others suggest that time travelers could be careful to avoid detection, or that history itself is self-correcting, preventing major changes from becoming noticeable. But there's another possibility. Perhaps time travel is impossible not because of paradoxes, but because of a deeper law of the universe that we do not yet understand. Some physicists speculate that there is a fundamental principle, like the second law of thermodynamics, that prevents backward time travel. Entropy, the measure of disorder in a system, always increases over time. A cup of hot coffee left alone will always cool down, never heat up spontaneously. Eggs break, but never unbreak. If the arrow of time is tied to the increase of entropy, then reversing time might require reversing entropy, something that has never been observed in nature. Perhaps time, as we experience it, is simply a byproduct of the universe's tendency toward disorder. If this is true, then traveling backward in time might not just be difficult, it might be fundamentally impossible. And yet, the question remains, if time is just another dimension, why can we only move in one direction? Why can we remember the past, but not the future? If the block universe is real and all moments exist equally, then what is special about now? Some physicists suggest that consciousness itself may play a role in defining time's arrow. Our brains process information in a way that gives us the sensation of a flowing present, even if reality is static. In this view, time doesn't move, we do. As you continue to drift in the void of space, watching the stars stretch infinitely before you, the answers seem just out of reach. The universe holds its secrets, waiting to be uncovered. Perhaps one day, we will unlock the mysteries of time and discover whether it is a force we can control or merely an illusion we can never escape. The closer you move to the event horizon of a black hole, the slower time flows for you relative to the outside universe. A clock on your wrist would tick normally from your perspective, but to a distant observer, it would appear to move slower and slower until, at the very edge of the event horizon, it would seem to freeze entirely. From the viewpoint of someone watching from afar, you would never truly cross into the black hole. You would simply slow down asymptotically, approaching a standstill in time. This extreme phenomenon is a direct consequence of gravitational time dilation, a prediction of Einstein's general relativity. The stronger the gravitational field, the more time stretches, bending under the weight of the universe's most extreme objects. If a deep enough gravity well can effectively halt time, could this be a natural way to travel into the distant future? If you hovered just outside the event horizon of a supermassive black hole for a few hours and then returned to Earth, you might find that thousands or even millions of years had passed for the rest of the universe. In a way, black holes act as one-way time machines, allowing passage to the future while trapping anything that dares venture too far. But if gravity can alter time, could it also be the key to reversing it? Could we manipulate gravitational fields in a way that allows time to loop back on itself? Physicists have considered this question, and some believe the answer might lie in the idea of closed, timelike curves, hypothetical paths in space-time that loop back to their own past. If such curves exist, they could theoretically allow an object, or even a person, to follow a trajectory that leads them backward in time. Some solutions to Einstein's equations suggest that under the right conditions, space-time could twist in ways that make time travel possible. One of the most famous of these solutions was proposed by the mathematician Kurt G. Dell in 1949. G. Dell discovered a model of the universe in which the entire cosmos was rotating. In this spinning universe, an object could take a specific path and arrive at a point in the past, creating a natural time loop. However, observations of our own universe show that it is not rotating in the way GDL's model requires, meaning this particular solution is not applicable to reality as we know it. Another attempt at solving the time travel equation came from Frank Tipler, who theorized that if an infinitely long, rapidly rotating cylinder existed in space, it could warp space-time in such a way that closed time like curves could form around it. If you traveled in a specific pattern around this cylinder, you could theoretically arrive at an earlier point in your own past. The problem? No such infinitely long cylinder exists, and even if one did, maintaining its stability would be nearly impossible. But perhaps there is another way. If time and space are interwoven, then extreme distortions in space should also distort time. This leads to one of the most fascinating ideas in modern physics, the wormhole. First predicted by Ludwig Flamm in 1916 and later explored in depth by physicists like Albert Einstein and Nathan Rosen, wormholes are theoretical bridges that connect two separate points in space-time. Unlike a black hole, which traps anything that falls in, a wormhole could serve as a shortcut between distant locations in the universe, or possibly even between different points in time. But wormholes present a number of challenges. First, they would require an exotic form of matter with negative energy to stay open. Without this, the throat of the wormhole would collapse instantly. Second, even if a wormhole could be stabilized, traveling through one would be incredibly dangerous, as tiny fluctuations could cause violent instabilities. However, if an advanced civilization or future human technology could find a way to create and maintain a traversable wormhole, it could become the ultimate tool for time travel. The idea is simple in theory. Suppose you take one end of a wormhole and accelerate it to near light speed while keeping the other end stationary. Due to relativistic time dilation, the moving end would experience time more slowly than the stationary end. If a traveler entered the stationary end, they could emerge from the moving end at an earlier point in time. Essentially, one end of the wormhole would be younger than the other, allowing for a form of backward time travel without violating the known laws of physics. But even if such a method worked, would it allow for unlimited travel into the past? Some physicists believe that wormhole time machines could only send travelers as far back as the moment the wormhole was created. This might explain why we don't see visitors from the future. If time travel becomes possible, it may only allow us to travel back to the point when the first time machine was invented, meaning no one could visit a time before that breakthrough. Yet, time travel remains elusive. The deeper we explore its possibilities, the more roadblocks we encounter. One of the most fundamental obstacles is the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases over time. If the arrow of time is tied to the growth of entropy, then reversing time might require reversing entropy itself, something that has never been observed in nature. Think of a shattered glass on the floor. In everyday experience, the broken pieces do not reassemble themselves. The glass does not spontaneously rise from the ground, whole and unbroken. The reason for this is entropy. Once disorder is created, it cannot be undone without external intervention. The universe as a whole seems to follow this rule, with entropy increasing from the Big Bang to the present. If time is just a consequence of this increase in disorder, then it might be fundamentally impossible to move backward, at least in any meaningful way. But quantum mechanics may offer a loophole. At the smallest scales of reality, particles do not behave in ways that align with our classical understanding of time. In the quantum realm, particles can exist in superpositions, being in multiple states at once. They can even become entangled, meaning that the state of one particle is instantly linked to another, no matter how far apart they are. Some interpretations of quantum mechanics suggest that at the most fundamental level, time may not exist at all. If time is not a fundamental property of reality, but instead emerges from deeper laws of physics, then it might be possible to manipulate or bypass it entirely. Some researchers speculate that quantum entanglement, the mysterious link between particles, could hold the key to understanding time travel. If information can be exchanged between entangled particles instantaneously, could this principle be extended to allow communication across time? Another intriguing idea comes from loop quantum gravity, a theory that attempts to reconcile general relativity with quantum mechanics. This framework suggests that space and time are not continuous, but instead made up of discrete, indivisible units. If this is true, then time is not a smooth river, but a series of individual moments, more like frames in a film than a flowing continuum. Some researchers believe this could allow for hopping between different moments in time, much like skipping between frames in a movie. But even if the mathematics allows for these possibilities, there is still no practical way to achieve them. The energy requirements, the engineering challenges, and the fundamental unknowns of quantum physics all present formidable barriers. The deeper we probe into time, the more elusive its true nature becomes. Yet, the questions remain. If time travel is theoretically possible, why haven't we seen any evidence of it? Are we missing some fundamental piece of the puzzle? Is time an unbreakable law, or is it simply another force waiting to be harnessed? As we push the boundaries of our understanding, one thing is certain: time is far stranger than we ever imagined. The more we study it, the more we realize how little we truly know. Perhaps the answers lie just beyond our reach, waiting to be discovered in the next great revolution of physics. If time is woven into the fabric of the universe, could it be something that can be stretched, manipulated, or even broken? We have seen that both motion and gravity affect time, yet the deeper we investigate, the more elusive its true nature becomes. Some physicists argue that time may not be fundamental at all, but rather an emergent property, something that arises from more basic physical principles rather than existing on its own. One of the strongest hints that time may not be fundamental comes from quantum mechanics, where the equations that govern the behavior of particles at the smallest scales do not require time to function. In classical physics, time is an essential ingredient. It tells us how things evolve from one state to another. But in the quantum world, some interpretations suggest that everything exists in a state of superposition, with multiple outcomes happening simultaneously until they are observed. If time were fundamental, it should be present in all physical laws, but certain quantum equations work just as well when time is removed altogether. This raises the question: if time emerges from something deeper, what does it emerge from? One possibility is entanglement, the mysterious connection between quantum particles that allows them to influence each other instantaneously, no matter how far apart they are. Some researchers believe that time may be a byproduct of entanglement, with the flow of time arising from the way information spreads across the universe. If this is the case, then time might not be an independent entity, but a consequence of how quantum systems interact with each other. Another attempt to explain time's emergence comes from loop quantum gravity, a theory that tries to merge general relativity with quantum mechanics. In this framework, space-time itself is quantized, made up of tiny, indivisible loops rather than being a smooth, continuous fabric. If space is quantized, then time may be as well, meaning that instead of flowing smoothly, it may progress in discrete steps, jumping from one moment to the next like frames in a film. If time is quantized, then our perception of a continuous flowing reality might be an illusion created by our brains, stitching together these discrete moments. This could explain why we only experience time in one direction. Our consciousness might be moving through these individual frames, giving us the illusion of movement and change. But could this also mean that time is not universal? Could different regions of the universe experience time differently, depending on the underlying quantum structures that define them? While quantum mechanics challenges our fundamental assumptions about time, relativity has also revealed deeper complexities. One of the most puzzling aspects of Einstein's theory is that it suggests time is relative, not just in the sense that it moves at different rates for different observers, but in the sense that there is no universal now. The idea that all moments in time exist simultaneously in the block universe interpretation raises the question: why do we experience only a single moment at a time? Some physicists propose that the reason we experience time as moving forward has to do with entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases, meaning the universe is constantly moving from a more ordered state to a more disordered one. This irreversible process gives us the illusion of a past that is fixed and a future that is yet to be determined. But why does entropy increase in only one direction? Some scientists have suggested that the arrow of time is set by the conditions of the early universe. If the Big Bang created a highly ordered state, then the natural progression toward greater disorder would give rise to the experience of time flowing forward. However, this explanation does not fully resolve the mystery. If time is truly just a result of increasing entropy, does that mean that in a universe where entropy reaches its maximum, time ceases to exist? Some researchers have explored the idea that there could be regions of the universe where time runs in reverse. In these regions, entropy would decrease instead of increase, meaning that from the perspective of an observer there, the past would appear as our future does, and vice versa. If true, this would mean that time is not a single, unified entity, but something that can behave differently in different parts of the cosmos. If time is something that can be reversed, does that mean events in the past can be altered? Theoretical physics suggests that even if traveling to the past were possible, nature might prevent any real changes from occurring. The Novikov self-consistency principle suggests that any action taken by a time traveler would already be part of history. In other words, even if someone were able to travel to the past, they would be unable to change anything in a way that creates a paradox. Their actions would always lead to the same outcome that history already recorded. Another possibility is that every choice made in the past or future creates a branching timeline. In this view, time is not a single sequence of events, but a constantly branching tree of possibilities. The many worlds interpretation of quantum mechanics suggests that every quantum event causes the universe to split, creating an infinite number of parallel realities. If this is true, then traveling to the past would not change our own timeline, but would instead create a new one, diverging from the original path. These ideas raise a profound question. If time is just one of many possible dimensions, could there be other forms of time beyond what we experience? Some theoretical physicists have proposed that our universe may be embedded in a higher dimensional structure where time behaves in ways we cannot yet comprehend. In certain string theory models, additional dimensions exist beyond the familiar three of space and one of time. If higher dimensional time exists, then our perception of past and future may be just a limited view of a far more complex temporal reality. One particularly strange hypothesis is that time could be cyclical, that rather than moving in a straight line from past to future, it could loop back on itself. Some cosmological models suggest that after the universe reaches a state of maximum entropy, it could collapse in a big crunch and restart in another big bang. If this cycle has happened before, then it raises the possibility that time is not linear, but part of an eternal loop, repeating endlessly with variations each time. If true, this would mean that our current universe may not be the first iteration of reality, but just one of an infinite series of cosmic cycles. It also raises the possibility that the laws of physics themselves may change over each cycle, meaning that time, as we understand it, may not always have existed in the same form. Could it be that time itself evolves over each iteration of the cosmos? Another radical idea suggests that time may not be fundamental to reality at all. Some physicists argue that space and time emerge from a deeper mathematical structure, one that does not require time to exist in the way we experience it. If this is the case, then time might not just be an illusion. It might not even be necessary to describe the universe at its most fundamental level. As our understanding of physics progresses, we may discover that time is far stranger than we ever imagined. It could be an emergent property, a side effect of deeper physical laws, or something that exists only in our perception rather than in reality itself. Whether time is fundamental or an illusion, whether it is linear or cyclical, whether it is absolute or relative, remains one of the greatest unanswered questions in science. But if time is not what it appears to be, then what does that mean for the way we understand existence itself? If time is an emergent or secondary effect of the universe's structure, then what lies beyond it? These questions remain at the forefront of theoretical physics, and every new discovery seems to challenge our assumptions about the nature of time and reality. No matter how we define time, whether as a physical dimension, an emergent property, or an illusion, our experience of it feels undeniably real. We are trapped in the present, remembering the past but unable to access the future. But why? Why? If the universe is a vast, unchanging block where all moments exist simultaneously, why do we experience time as flowing forward, one moment at a time? The way we perceive time is unique among all our senses. Sight, sound, and touch provide us with immediate information about the world, but time is different. We don't just perceive it, we exist within it. We have memories of what came before, but we cannot recall the future. We can plan ahead, but we can never be certain what will happen. The subjective passage of time shapes every aspect of our lives, yet we have little understanding of why we experience it at all. Some scientists believe that our perception of time is a byproduct of how our brains process information. Unlike a clock, which marks time in steady, predictable intervals, the human mind does not experience time uniformly. In moments of danger, time seems to slow down, stretching seconds into what feels like minutes. During intense focus, we lose track of time completely. And in dreams, time becomes meaningless. Hours can pass in the real world while entire lifetimes seem to unfold in the mind. The brain does not passively observe time, it constructs it. Neuroscientists have found that different regions of the brain contribute to our sense of temporal flow. The hippocampus, responsible for memory, allows us to place events in chronological order. The prefrontal cortex, which governs decision-making, helps us predict the future. The cerebellum plays a role in fine-tuning our internal clock, helping us perceive time intervals accurately. But perhaps the most fascinating insight comes from the idea that consciousness itself may be responsible for the experience of time. Some researchers suggest that our awareness does not exist in a single moment, but is instead stretched across a small window of time, a concept known as the specious present. This means that the now we experience is not a single point, but a short interval, during which our brain integrates past and present information to create the illusion of continuity. This could explain why time appears to flow smoothly. If our brains process moments in overlapping sequences, then the present moment is always a blend of the immediate past and an expectation of the near future. This might be why we perceive motion rather than a series of still images. If we only experienced individual moments without continuity, reality would feel fragmented, like watching a film frame by frame rather than as a continuous story. But if time is just a construct of the brain, what does that mean for the objective nature of time itself? Some physicists argue that if consciousness creates the illusion of time flowing forward, then time, as we perceive it, may not be fundamental at all. In this view, the universe does not move through time. Rather, our minds create the illusion of motion. This idea is closely tied to quantum mechanics, which suggests that the smallest particles in the universe do not experience time in the same way that we do. At the quantum level, particles exist in a state of probability until they are observed. Some interpretations suggest that time does not advance in the quantum world. It simply exists as a static backdrop, and only when an observer interacts with it does reality take on a definite state. One of the strangest phenomena in quantum mechanics is quantum entanglement. When two particles become entangled, they share information instantly, regardless of the distance between them. If one particle is measured, its entangled partner reflects the same measurement, even if they are separated by vast cosmic distances. This seems to defy classical notions of time. If information can be transferred instantaneously, does that mean time is irrelevant at the quantum level? Some physicists speculate that our experience of time may emerge from the way quantum systems interact. Instead of time being fundamental, it could be a consequence of entanglement spreading through the universe. This idea, known as the quantum origin of time, suggests that time is not an absolute feature of reality, but a side effect of how particles interact with each other. This raises an even deeper question. If time is an emergent property, could there be forms of consciousness that exist outside of time? Our awareness is bound to the passage of time because our brains process information in sequence. But could there be minds, whether artificial, biological, or something beyond our comprehension, that experience all of time at once? Some speculative theories suggest that if an intelligence existed in a higher dimension beyond our three-dimensional space, it might perceive time differently. Just as we can see an entire landscape at once, while an ant on the ground experiences it one step at a time, a being outside of time might view the past, present, and future as a single, unbroken whole. If this were the case, would such a being have free will? Or would it be forever locked into seeing every possible outcome at once? The question of free will becomes even more complex when considering the implications of a deterministic universe. If time is already written, if the past and future are just as real as the present, then every choice we make may already be set in stone. From a block universe perspective, the sensation of making decisions is simply a consequence of our minds moving along a predetermined path through time. Yet, the unpredictability of quantum mechanics suggests that randomness plays a role in shaping the future. If quantum events are truly random, then not everything is determined, and there may still be room for free will. But randomness does not equal control. If our decisions are influenced by quantum fluctuations, are they truly our choices, or are they just the result of chance? This debate extends into neuroscience, where studies have shown that decisions can often be predicted before a person is even aware of making them. In experiments, researchers have observed brain activity indicating a choice seconds before the individual consciously decides. This suggests that our sense of decision-making may be an after-the-fact illusion, with our brains preparing actions before we become aware of them. But is this truly evidence against free will, or is it simply a reflection of the way consciousness operates? Some argue that consciousness is not separate from the brain, but an integrated process that includes unconscious decision-making. If the brain processes information in stages, then what we call a decision may be the final step in a much larger sequence of events. Others take a different perspective, arguing that free will is an emergent property of complex systems. Just as time may emerge from deeper physical laws, free will may emerge from the intricate interactions of neurons, thoughts, and experiences. Even if the universe follows deterministic rules at the fundamental level, the sheer complexity of the human mind may allow for a form of self-determination that feels indistinguishable from true free will. The relationship between time and consciousness remains one of the greatest mysteries in science. We experience time as something constant, yet physics suggests it is anything but. We believe in the power of choice, yet our own brains may be making decisions before we even realize it. If time is truly an illusion, then our entire perception of existence may be nothing more than a construct, a way for our minds to organize reality into something understandable. But if time is not fundamental, then what is? If consciousness requires time to function, then what happens if time ceases to exist? These questions remain unanswered, but they continue to push the boundaries of our understanding, revealing a universe that is far stranger than we ever imagined. Imagine a universe where time has stopped, not slowed down due to gravity, not stretched by velocity, but truly frozen. In this universe, no stars burn, no planets orbit, and no thoughts form. Everything is locked in a single, eternal moment. But does such a place truly exist? Or is it only a thought experiment, a glimpse into the very limits of time itself? For centuries, humans have assumed that time is an inherent part of reality, something as fundamental as space and matter. Yet, modern physics suggests that time may not be as essential as we once believed. Could there be regions of the cosmos where time behaves differently, or even ceases to exist altogether? And if so, what would that mean for everything we understand about the universe? One of the most extreme examples of time behaving strangely can be found at the event horizon of a black hole. To an outside observer, an object falling into a black hole appears to slow down, its movement becoming increasingly sluggish as it nears the event horizon. At a certain point, it seems to freeze, forever hovering at the edge. From the perspective of the falling object, however, time flows normally. It crosses the event horizon and continues toward the singularity at the black hole's core. But to the rest of the universe, it remains suspended in time, never quite vanishing from view. This is a direct result of gravitational time dilation, the warping of time caused by extreme gravity. The more intense the gravitational field, the slower time moves. But if a black hole's event horizon slows time to the point of appearing frozen, what happens inside? Some theories suggest that beyond the event horizon, time and space switch roles, meaning that moving forward in time is equivalent to moving toward the singularity. If this is true, then falling into a black hole may mean being trapped in a reality where time, as we know it, no longer makes sense. But black holes are not the only places where time's rules may break down. Some cosmologists have proposed that the universe itself may experience regions of timelessness, places where time effectively stops or never began. One such possibility is found in the study of the Big Bang itself. The standard model of cosmology suggests that time began at the moment of the Big Bang, roughly 13.8 billion years ago. But what does it mean for time to have a beginning? If time had a starting point, then asking what came before the Big Bang might be meaningless, much like asking what's north of the North Pole. But some theories suggest that time may have existed before the Big Bang in some form, or that it may emerge periodically in cycles, giving rise to a universe that expands, contracts, and then begins again. One such model is the cyclic universe hypothesis, which proposes that the universe goes through endless cycles of expansion and collapse. In this scenario, time might reset with each cycle, meaning that what we perceive as the beginning of time is simply one point in an infinite sequence of cosmic rebirths. If this is true, then time may be far older than we assume, perhaps infinitely old, with no true starting point at all. On the other end of the cosmic timeline is the heat death of the universe, a scenario in which the universe continues expanding indefinitely until it reaches a state of complete thermodynamic equilibrium. In this state, entropy, the measure of disorder, would reach its maximum, and all useful energy would be evenly distributed. Without energy differences to drive motion, no chemical reactions, no star formation, and no meaningful events could occur. In essence, time would cease to have any real function because nothing would change. This idea raises a strange possibility. If time is tied to change, then in a universe where nothing changes, does time even exist? If the future heat death of the universe results in absolute stillness, does that mean time itself will stop? Some physicists argue that in such a scenario, time would become meaningless, not because the universe would no longer exist, but because there would be no reference points left to distinguish one moment from another. But what if time does not simply end, but instead reverses? Some theories suggest that at the extreme limits of entropy, the direction of time could flip, leading to a universe that runs in reverse, eventually returning to its original state before beginning the cycle again. If this were the case, would it mean that our entire existence is destined to repeat, endlessly cycling through the same moments over and over? The possibility of a cyclic time loop is not just a feature of cosmology, it also appears in some interpretations of quantum mechanics. One of the strangest ideas in modern physics is the concept of retrocausality, which suggests that the future might influence the past. In most scientific models, causality moves in one direction, causes lead to effects. But in some quantum experiments, particles appear to behave as though information from the future is affecting their past states. If this is the case, could time be more flexible than we assume? Could it be possible that future events ripple backward, shaping history in subtle ways? Another area where time behaves strangely is in the study of time crystals, a recently discovered phase of matter that defies conventional physics. Unlike ordinary crystals, which have repeating structures in space, time crystals have repeating structures in time. This means that their atomic states oscillate in a regular, repeating pattern without consuming energy, effectively creating a system where motion exists even in a state of equilibrium. The discovery of time crystals suggests that time may not be a singular, continuous flow, but something that can exist in discrete states, much like matter itself. If time can crystallize into a repeating pattern, could there be other exotic phases of time that we have yet to uncover? Could there be materials, structures, or even entire universes where time functions in a completely different way? Some physicists have proposed that what we call time is simply a byproduct of a deeper reality, one where time, space, and even causality itself are secondary effects of a more fundamental system. In this view, time may not be something that flows, but rather a quality that emerges when certain conditions are met, much like temperature arises from the motion of particles. One radical theory suggests that time is an illusion created by consciousness itself. According to this idea, the past, present, and future all exist simultaneously, but we experience them sequentially because of how our minds process information. If this is true, then time is not an external force, but a construct of perception. Some researchers have even proposed that under the right conditions, such as altered states of consciousness or near-death experiences, individuals may briefly step outside the normal flow of time, experiencing it in a way that defies conventional understanding. Yet, despite these theories, the fundamental nature of time remains one of the greatest unsolved mysteries in physics. Every attempt to explain it leads to deeper questions. Is time a dimension, a force, an emergent property, or something beyond our current understanding? If time began, what existed before it? If time ends, what comes after? Even as our understanding of the universe advances, time continues to elude us. It governs every moment of our lives, yet we have no way to truly grasp what it is. Perhaps time is not something to be measured, controlled, or even fully understood, but something that defines the very essence of existence itself. Here is something unsettling about the way time works. It is the only thing we can never escape, yet we barely understand it. We can cross great distances in space, but no matter what we do, we remain prisoners of the present. The past is untouchable, the future uncertain. But what if there were a way to break free? What if time is not what it appears to be? The deeper we probe into time, the more paradoxes emerge. Take, for instance, the mystery of the observer effect in quantum mechanics. Experiments suggest that a particle does not take on a definite state until it is observed. Before measurement, it exists in a superposition of multiple possibilities, all equally real. But the moment we look at it, the possibilities collapse into a single outcome. This raises a disturbing question. Does the past exist before we observe it? If a quantum particle state is not determined until measured, then could the past itself be fluid, only solidifying when we look back at it? Could history be rewritten not through time travel, but through observation itself? Some physicists argue that the past is not as fixed as we assume. In certain quantum experiments, choices made in the present seem to influence past events. This idea, known as retrocausality, suggests that time might not be strictly linear. It hints at a reality where cause and effect are tangled, where the future can ripple backward and reshape history in subtle ways. This isn't just a theoretical oddity. It has been observed in experiments. In the delayed choice quantum eraser experiment, particles appear to decide how they behaved in the past based on measurements made in the present. It's as if reality adjusts itself retroactively, erasing or rewriting events depending on how they are later observed. If this effect operates at larger scales, it could mean that our perception of an unchangeable past is just an illusion. What we think of as history may not be an immutable record, but a constantly shifting pattern of probabilities, solidifying only when we turn our attention to it. If true, this would upend everything we believe about time, causality, and reality itself. Another puzzle emerges when we look at the information paradox, a conflict between quantum mechanics and general relativity. According to Einstein, anything that falls into a black hole is lost forever. The information it carried, whether it was a planet, a star, or even a person, is erased from existence. But quantum mechanics insists that information can never be destroyed. This contradiction suggests that either our understanding of gravity is incomplete or our understanding of time is flawed. Some physicists believe that information is never truly lost, but is instead encoded on the event horizon of a black hole, stored in a two-dimensional form. This idea, known as the holographic principle, suggests that everything we experience as reality, including time itself, might be nothing more than a projection of information stored on the edges of the universe. If this is true, then time may not be a fundamental part of reality at all. Instead of a flowing river, time could be a construct, a secondary effect of a deeper, timeless reality. We may only perceive time because we are trapped inside a system that forces us to experience events in sequence. If we could step outside this system, we might see the entire structure of the universe laid out at once, with no distinction between past, present, and future. But even if time is an illusion, it is a persistent one. Our brains are wired to experience time in a linear fashion, and breaking free from this perception seems impossible. But could there be beings, whether advanced civilizations, artificial intelligences, or even unknown life forms, that experience time differently? Some scientists speculate that if consciousness emerges from quantum processes, then an intelligence that operates at a quantum level could perceive time in ways that are incomprehensible to us. Instead of moving through time moment by moment, such an intelligence might exist across multiple moments simultaneously, experiencing the past, present, and future as a single, unbroken reality. This idea is not entirely foreign to human experience. In certain altered states, such as deep meditation, psychedelic experiences, or near-death encounters, people have reported sensations of time slowing, stopping, or even ceasing to exist altogether. Some describe the feeling of seeing their entire life all at once, as if past and future were no longer separate. Could these experiences hint at a hidden aspect of consciousness, one that momentarily breaks free from the constraints of linear time? Another mind-bending concept is the idea that time may be directionless at the deepest level of physics. While we experience time as moving forward, many fundamental laws of physics work just as well in reverse. If time is simply another dimension, like space, then why do we experience it with a built-in direction? One possible explanation is the arrow of time, which is closely tied to entropy. The universe began in an extremely low entropy state and has been increasing in disorder ever since. This increasing entropy gives rise to the sensation of time moving forward. But what if the universe is part of a larger system where entropy can decrease? Some theories suggest that another region of the universe may experience time in reverse, with entropy decreasing instead of increasing. If this is true, then there may be an entirely separate reality where everything we know is happening backward, where people grow younger, broken objects reassemble, and cause follows effect instead of the other way around. But could we ever communicate with such a reality? If time can flow in both directions, could it be possible to send information across the divide? Some researchers speculate that quantum entanglement might provide a bridge between forward and backward time, allowing us to exchange information with a reversed version of reality. If this were the case, then messages from the future might not require a time machine at all. They could already be embedded in the very fabric of the quantum world, waiting to be deciphered. These ideas push the limits of what we consider possible, yet they are grounded in real scientific research. The more we study time, the stranger it becomes. Whether time is a fundamental property of the universe, an emergent effect, or an illusion created by consciousness, one thing is certain: we are only beginning to scratch the surface of its mysteries. For now, we remain trapped in the present, unable to see beyond the veil of the future or reach back into the past. But if the universe holds secrets about time, then it is only a matter of discovery before we unlock them. And when that day comes, time itself may never be the same again. If time travel is possible, then where are the travelers? It is a question that lingers at the edge of scientific and philosophical debate. We have explored time's mysteries, from relativity to quantum mechanics, from paradoxes to the very nature of reality itself. Yet, despite all our theories, we have never seen definitive proof of someone stepping out of the past or arriving from the future. Does this mean time travel is impossible, or does it mean we simply do not yet understand how to unlock it? Science tells us that traveling forward in time is not only possible, but already happens, at least in small ways. Every astronaut aboard the International Space Station experiences time slightly more slowly than those on Earth. High-speed particles moving close to the speed of light age, more slowly than we do. In theory, if a human could travel fast enough, nearing the speed of light, they could leap forward centuries into the future while experiencing only a few years themselves. This much is allowed by physics. But traveling backward in time is where the real challenges arise. General relativity does not strictly forbid it. Certain solutions in Einstein's equations allow for closed timelike curves, paths through space-time that loop back on themselves. Wormholes, if they can be stabilized, could theoretically create a tunnel between different points in time. Yet, no natural wormholes have ever been discovered, and no experiment has shown that time can be manipulated in this way. The deeper issue may not be the mechanics of time travel, but the paradoxes it creates. The grandfather paradox, the bootstrap paradox, and questions of free will all cast doubt on the idea that time can be rewritten. If time travel were possible, could we really change history? Or would time be self-correcting, ensuring that all events unfold exactly as they always have? Some physicists believe the universe prevents paradoxes by enforcing self-consistency. If you were to go back in time, everything you do would already be part of history. This would mean that even if time travel exists, it could not be used to alter the past, only to become part of it. Others propose that time travel, if real, would create branching timelines rather than altering the same one. This would mean that traveling to the past creates an alternate reality rather than changing the present. If this is true, then every moment in time might already exist as part of a vast multiverse, where every choice and every possibility unfolds somewhere. But perhaps time is not something we can travel through at all. Perhaps time is not a road, but an illusion, something created by consciousness rather than something that exists independently. Quantum mechanics suggests that at the smallest scales, time behaves differently than we expect. Some researchers even propose that time does not truly exist at the fundamental level of reality. If this is the case, then what we perceive as time may simply be a byproduct of the way our minds interpret the universe. If time is an illusion, then what does that mean for our place in the cosmos? Are we simply trapped in a perception of reality that is not real? Or does the very nature of existence depend on our ability to experience time? The universe is vast, mysterious, and filled with unanswered questions. Whether time is a force, an illusion, or a property of consciousness, one truth remains: we exist within it, moving forward one moment at a time, unable to pause, rewind, or jump ahead. For now, time remains the great boundary we cannot cross. But history has shown us that what seems impossible today can become reality tomorrow. The question is not just whether time travel is possible, but whether we will one day discover the key to unlocking it. You are aboard a spacecraft, floating in the silent abyss of interstellar space. The stars outside your window are ancient, their light stretching across millions of years to reach you. Every movement, every signal sent from your ship takes time, minutes, hours, even years to travel across the cosmic void. But then something impossible happens. A message appears on your screen instantly. Not carried by radio waves, not transmitted through light, but teleported, its information woven into the very fabric of quantum reality. It did not travel the distance between its origin and your ship. It simply appeared. This is not science fiction. It is the reality of quantum teleportation, a process where information, not matter, is transferred instantaneously, breaking the traditional rules of space and time. Unlike the teleporters of futuristic movies, quantum teleportation does not transport objects or people, but rather the essence of their quantum state, the fundamental information that defines them. But how is this possible? How can something leap across space without physically moving? To answer this, we must journey into the depths of quantum mechanics, where particles exist in multiple states at once, where entanglement links objects across vast distances, and where reality itself appears to be nothing more than a fragile web of probabilities. This is the story of quantum teleportation, a phenomenon that challenges the very nature of existence, a discovery that could one day revolutionize communication, computing, and perhaps even our understanding of the universe itself. But before we can unlock the secrets of teleportation, we must first understand the bizarre quantum world that makes it possible. There was a time when physics was simple. Objects had precise locations, forces acted predictably, and the universe followed clear, mechanical laws. Then, quantum mechanics arrived, a theory so strange that even Einstein struggled to accept it. A theory that shattered our most fundamental assumptions about reality. At the heart of this revolution lies a disturbing truth. At the smallest scales, the universe does not behave in any definite way until we observe it. To understand why, picture a marble rolling across a smooth table. In the classical world, if you knew its exact position and velocity, you could predict where it would be at any future moment. But in the quantum world, the marble does not have one definite position. It has many at once. It exists everywhere it could possibly be, in a superposition of states. It is only when someone looks that the marble chooses a location. This is not just a mathematical trick. It is an experimental fact. Scientists have observed single particles interfering with themselves as if they were passing through multiple paths simultaneously. The famous double-slit experiment demonstrates this with eerie clarity. A beam of electrons is fired at a barrier with two narrow slits, and a detector screen is placed behind it. If electrons were simple particles, they would pass through one slit or the other, forming two clusters on the screen. But that's not what happens. Instead, they form an interference pattern as if each electron passed through both slits at once, behaving like a wave. This means that before measurement, an electron is not in one location, but in all possible locations at the same time. Only when a detector is placed near the slits, forcing the electron to be observed, does it suddenly decide which path to take, destroying the interference pattern. The act of measurement itself changes reality. But if superposition is strange, what comes next is even stranger. Imagine two particles born from the same quantum event. They fly apart, separated by miles, even light years. And yet, if we measure one, the other instantly knows what happened. This is quantum entanglement, a phenomenon so bizarre that Einstein famously called it spooky action at a distance. Entanglement suggests that two particles, no matter how far apart, are fundamentally connected. If one is found spinning clockwise, the other will always be counterclockwise, instantly, without any signal traveling between them. This should be impossible. Information cannot travel faster than light, yet entanglement seems to bypass this rule entirely. Einstein was convinced that something deeper was at play. He believed quantum mechanics was incomplete and that hidden variables, some unseen properties of particles, were secretly guiding their behavior. If such variables existed, then entangled particles were not truly influencing each other instantaneously. Instead, they had always possessed predetermined states, like two coins flipped in secret before being revealed. For decades, this question lingered. Was quantum mechanics truly random, or was there an underlying order hidden from view? Then, in 1964, physicist John Bell devised an elegant test, one that would prove, once and for all, whether hidden variables existed. His idea, Bell's theorem, established a mathematical inequality. If hidden variables controlled quantum systems, then measurements of entangled particles would follow classical statistical rules. But if quantum mechanics was correct, if reality was fundamentally indeterminate, then entanglement would violate Bell's inequality, showing correlations that no classical system could explain. Bell's theorem turned quantum weirdness into something testable. And when experiments were finally performed, the results were undeniable. Bell's inequality was violated. Time and time again, entangled particles defied classical expectations. The results could not be explained by hidden variables. The universe was not deterministic. Quantum mechanics was not just a strange approximation of reality, it was reality. This revelation was profound. It meant that at its core, the universe is governed not by rigid laws, but by probabilities. A particle's properties are not fixed until measured. And once measured, entangled particles communicate their states instantaneously, defying space itself. But why does this matter for teleportation? Because entanglement is the key to transferring quantum information across space. Teleportation is not about moving objects from one place to another. Instead, it's about transferring a quantum state, the very essence of a particle's identity, without sending the particle itself. And to do this, we must use entanglement in a way that seems almost paradoxical. First, we start with an entangled pair of particles. One particle is kept at the sender's location, and the other is sent to the recipient. Now, a third particle, the one we want to teleport, is introduced at the sender's end. This particle interacts with the sender's entangled particle, collapsing both of their states in a way that destroys the original information. At this moment, the quantum state of the third particle is erased from existence, but its information has been imprinted onto the distant entangled particle. The recipient does not yet have access to this information, though. To complete the process, a classical message must be sent, instructing the recipient on how to manipulate their particle to match the original state. Once these adjustments are made, the recipient's particle becomes identical to the one that was destroyed. This is teleportation, not in the science fiction sense, where objects physically travel, but in a deeper, more unsettling way. The original disappears, and its essence is reborn elsewhere. But there's a critical limitation. Teleportation cannot be used to send information faster than light. The classical message containing the necessary corrections must still travel through normal space. This means that while the quantum state transfers instantly, we cannot use teleportation for superluminal communication. However, this does not make the process any less remarkable. Quantum teleportation relies entirely on the non-local nature of reality, the fact that entangled particles do not behave as separate entities, but as a unified system. This is only possible because Bell's theorem shattered the last hope of hidden variables. If Einstein had been correct and particles had predetermined states, teleportation would not work. But because quantum mechanics is inherently probabilistic, teleportation becomes a fundamental part of nature's design. And this raises a disturbing question. If reality is connected on such a deep level, then what does it mean for our perception of space and time? Some physicists believe that space itself is an illusion, that distance is not a fundamental property of the universe, but an emergent effect of entanglement. In this view, teleportation does not send information across space at all. Instead, it exploits the fact that everything may already be connected beyond what we can perceive. This idea is still speculative, but it aligns with a growing perspective in physics that space-time itself is built from the fabric of entanglement. If true, then quantum teleportation is not just a technological trick, but a glimpse into the deeper structure of the universe itself. For now, the practical applications of teleportation remain in their infancy. Scientists have successfully teleported photons, atoms, and even small molecules. Future experiments aim to scale this up, building quantum networks that could revolutionize computing and communication. But as we push further, we are forced to confront unsettling implications. Teleportation erases the original and reconstructs it elsewhere. If one day we teleport complex objects, or even conscious beings, what would that mean? Would the person on the other side still be the same? Or would they be something new? The answers remain elusive. But one thing is certain, quantum mechanics has rewritten the rules of reality. And teleportation is just the beginning. A locked vault sits in front of you. Inside, there is a letter, one you are not allowed to open. You cannot read its contents, cannot photocopy it, cannot take it out of the vault. But you must send its exact message to a friend on the other side of the world. Not a summary, not a copy. The original information itself must reach them without ever physically moving the letter. If this sounds impossible, welcome to the paradox of quantum teleportation, a process that allows information to transfer from one place to another, not by sending it, but by erasing it from one location and reconstructing it elsewhere. But how does this actually work? It all begins with a single quantum state, the defining signature of a particle. Unlike classical information, which exists in well-defined units, quantum information is fragile, bound by the strange laws of uncertainty. A particle's properties, such as its spin or polarization, are not set in stone. They exist in a delicate, ever-shifting superposition of possibilities. If we attempt to measure this information directly, we destroy its original form. Unlike a printed document that can be copied without altering the text, quantum information cannot be duplicated. The no-cloning theorem, a fundamental law of quantum mechanics, states that an unknown quantum state cannot be perfectly copied. The moment we try to make an exact replica, the original state collapses, irreversibly lost. This presents a problem. If quantum states cannot be measured without being disturbed, and if they cannot be copied, then how can they be transferred across space? The answer lies in the only known method of circumventing these restrictions: quantum teleportation. Teleportation begins with an essential ingredient: entanglement. Before any transfer of quantum information can happen, we must create a link between two distant locations. This is done by generating a pair of entangled particles, two quantum objects so deeply connected that their states are intertwined, regardless of the distance between them. One of these particles is kept at the sender's location. The other is sent to the receiver. Despite being physically separated, they remain part of the same quantum system. Now, a third particle, the one carrying the quantum state we want to teleport, is introduced. This particle interacts with the sender's entangled particle, undergoing a carefully controlled quantum operation known as a Bell state measurement. The moment this measurement occurs, something remarkable happens. The original quantum state, previously held by the third particle, is completely erased. It no longer exists at the sender's location. Instead, its essence has been transferred to the entangled particle on the receiver's side. But there is still a missing piece. The receiver's particle has now absorbed the quantum information, but it remains in an incomplete, scrambled form. To restore the original quantum state perfectly, an additional step is required. A classical message must be sent from the sender to the receiver. This message contains 2 bits of information, just enough for the receiver to know how to adjust their particle. Once these adjustments are applied, the receiver's particle becomes a perfect replica of the original, containing the same quantum state that was destroyed at the sender's end. The teleportation is now complete. But what makes this process so strange is that nothing physical traveled between the 2 locations. The quantum state did not move. The particle at the receiver's end was never in contact with the original. And yet, somehow, the exact quantum information was reconstructed with perfect fidelity. This raises a fundamental question: where was the information before it arrived? One interpretation suggests that quantum states do not exist in a fixed location. Instead, they are non-local entities, patterns of probabilities spread across space. When teleportation occurs, the information does not travel in the conventional sense. It simply rearranges itself, shifting from one particle to another in a way that our classical understanding of space cannot explain. Another perspective comes from quantum field theory, which suggests that particles are not fundamental objects, but excitations of an underlying quantum field. If this is true, then teleportation is not moving something from point A to point B. Rather, it is an operation on the underlying field itself, causing the quantum state to manifest in a new location while disappearing from the old one. Regardless of interpretation, quantum teleportation is not instantaneous communication. The process relies on a classical message to complete the transfer, which means it cannot be used to send signals faster than light. The quantum state may transfer instantly, but the receiver cannot access it until the classical information arrives. This limitation prevents teleportation from violating Einstein's theory of relativity, but it does not make the process any less revolutionary. Quantum teleportation has already been demonstrated in laboratories, with particles successfully teleported over distances exceeding 1,400 kilometers. Future experiments aim to extend this to even greater distances, using satellites to establish global-scale quantum networks. One of the most promising applications of teleportation lies in quantum cryptography. Because quantum information cannot be copied or intercepted without being destroyed, teleportation can be used to create ultra-secure communication channels. Any attempt to eavesdrop on a quantum transmission would be immediately detected, making it theoretically impossible to hack. Beyond cryptography, teleportation plays a crucial role in quantum computing. Unlike classical computers, which process information in binary, 0s and 1s, quantum computers use qubits, quantum bits that can exist in multiple states at once. Teleportation allows qubits to be transferred between quantum processors without ever being measured, enabling distributed quantum networks that vastly outperform traditional computing systems. Yet, teleportation still faces immense technical challenges. One of the biggest obstacles is quantum decoherence, the tendency of quantum states to degrade when exposed to their environment. Even the smallest disturbances, such as thermal noise or stray electromagnetic fields, can disrupt entanglement, rendering teleportation unreliable. To overcome this, scientists are developing error correction techniques and quantum repeaters, devices that extend entanglement over vast distances, ensuring that teleportation remains stable across large-scale networks. These advances could eventually make teleportation a routine part of data transmission, replacing conventional encryption methods with an unbreakable quantum internet. But perhaps the most profound implication of quantum teleportation is its impact on our understanding of identity and existence. If a quantum state can be destroyed and perfectly reassembled elsewhere, what does that mean for objects or even conscious beings? If, one day, we learn to teleport the quantum state of a complex structure, would the object at the destination be the same as the one that was destroyed? Or would it be an identical copy, while the original ceases to exist? These are not just philosophical musings. The laws of quantum mechanics are clear. Teleportation does not duplicate, it transfers. If extended to macroscopic scales, it could challenge our deepest assumptions about what it means to be the same entity. Quantum teleportation transfers information, not matter. Atoms are not physically sent from one place to another. Instead, their quantum states are destroyed in one location and reconstructed elsewhere. This is fine for particles, but when applied to something as complex as a human mind, it raises profound and unsettling questions. If the quantum state of a person's brain could be teleported, what would that mean for their consciousness? Would the person who arrives at the destination truly be the same individual, or would the original self have ceased to exist? A key issue is the no-cloning theorem, a fundamental rule of quantum mechanics that prevents an exact copy of an unknown quantum state from being made. This means that if teleportation were applied to a human, there would be no backup copy of their consciousness. The process would involve the destruction of the original state, ensuring that only one version remains. But what does this destruction actually mean? Some argue that consciousness is nothing more than a pattern of information. If the neural connections and quantum states of a brain can be perfectly replicated, then subjective experience should continue seamlessly, just as it does when the brain undergoes changes during sleep or unconsciousness. From this perspective, teleportation would be no different from walking across a room. The continuity of self is simply preserved in a new location. But this assumption is deeply troubling. If a machine could scan a person and reconstruct them elsewhere, what happens if the original is not destroyed? Suppose a teleportation system malfunctions, and instead of erasing the first version, it creates a second. Now, two identical people exist. Each one shares the same memories, the same thoughts, the same sense of self. But only one can be the true original, if such a concept even exists. This thought experiment highlights a fundamental problem. Identity is not just about structure, but also about continuity. The copy believes it is the original because it has the same memories and personality. But would the first version experience a break in consciousness when the copy is made? If the first version is then eliminated, would that be equivalent to death? One possible answer comes from neuroscience. The brain is constantly in flux. Neurons fire, connections form and break, and yet, through all these changes, we perceive a continuous self. This suggests that the self is not tied to specific atoms, but rather to the pattern of activity in the brain. If teleportation preserves this pattern exactly, then functionally, there should be no difference between stepping into a teleporter and falling asleep, except that waking up would occur in a new location. But there are other possibilities. Some interpretations of consciousness suggest that subjective experience is irreducible, that it arises from quantum processes in the brain that cannot simply be transferred. Theories like orchestrated objective reduction, OR, propose that consciousness is not just computation, but is tied to quantum coherence, occurring in microtubules within neurons. If this is true, teleportation could fail in an unexpected way. The new version would still think and behave identically, but it would lack the same conscious awareness as the original. The person would appear normal, but the spark of subjective experience, the thing that makes someone feel alive, might not carry over. A different issue arises when considering time and perception. What if teleportation takes an individual apart, but due to an error, the reconstruction is delayed by 10 minutes? For those 10 minutes, would the individual exist in a state of nothingness, or would they simply experience an instantaneous jump forward in time? If the original is erased and the reconstruction never happens, would the person have truly died, or would it simply be as if they never stepped into the machine at all? Such questions challenge not only physics, but also the very definition of what it means to be alive. If teleportation were ever applied to humans, it would force society to redefine identity, continuity, and personal survival. Would legal systems consider the teleported version as the same individual? Would people willingly step into a machine that destroys them on one end, knowing that an identical version will emerge elsewhere? Would teleportation become a common means of travel, or would it be seen as a form of high-tech suicide? The implications extend beyond individuals to society as a whole. If consciousness can be transferred, then could it also be stored? Could minds be backed up like digital files and later restored into new bodies? Could people have multiple versions of themselves in different places, sharing the same experiences until they diverge into separate identities? If so, teleportation is no longer just a means of travel. It becomes a method of immortality. At the same time, teleportation could completely change the nature of work, relationships, and personal interactions. A person could send themselves to a distant location without physically traveling, experiencing another part of the world instantly. Business meetings, education, even social interactions could take place in entirely new ways. But this also raises ethical concerns. Could someone's mind be copied without their consent? Could an unauthorized teleportation process be used to create duplicate individuals, leading to identity disputes? Another unresolved issue is the potential psychological impact of teleportation. Even if people trust the process, would stepping into a teleportation machine induce existential dread? Would some individuals develop a deep fear of discontinuity, refusing to use teleportation despite its convenience? Would societies develop new cultural attitudes around identity, with some people embracing teleportation as an enhancement, while others reject it entirely? The more we explore teleportation's effects on consciousness, the more unsettling it becomes. If the brain is merely a collection of quantum states, then in theory, teleportation is just a transfer of information. But if consciousness requires an unbroken flow of experience, then teleportation might be something else entirely, a process that creates an identical copy while extinguishing the original. The fundamental question remains, is teleportation the movement of a person, or is it the destruction of one and the creation of another? At its core, this debate forces us to confront the possibility that our sense of self is a fragile illusion, one that quantum teleportation threatens to expose. If identity is just a pattern, then the process works. But if there is something deeper, something beyond mere structure, then teleportation may never be anything more than the most sophisticated copy machine ever invented. Perhaps the only way to know for certain is to try it. A teleportation system is activated. The process is flawless. Quantum states are erased in one location and reconstructed elsewhere. The individual steps in, disappears, and reappears in a different place, identical in every way. Everything works as expected. But what if, by some quantum chance, the original was not erased? What if, instead of one perfect reconstruction, two identical versions continue to exist, each believing they are the original? Teleportation presents a terrifying paradox. If consciousness is tied to physical matter, then only the body that emerges at the new location should be considered real. But if the mind is simply a pattern of quantum states, then both versions, the one that continued to exist and the one that was teleported, would believe they are the same person. Which one holds the true identity? And if two exist, what happens when one of them dies? This question leads directly to a concept known as quantum immortality. If reality branches due to quantum mechanics, then every decision, every event, creates multiple possible outcomes. Some interpretations suggest that consciousness follows only the paths where it survives. That is, no matter how many versions of you cease to exist, there will always be at least one where you continue. This suggests that, from a first-person perspective, you will never experience death, only an unbroken chain of survival through increasingly improbable circumstances. Teleportation complicates this idea further. If the original is destroyed and the copy continues, does this count as a seamless transition? If, in some fraction of cases, the original is not destroyed, does that mean the person stepping into the teleportation device always survives somewhere? If so, teleportation may not be a simple movement from one place to another, but rather a branching of existence itself. Imagine a future where teleportation is as common as air travel. People step into teleporters, believing they are traveling across the world. But in some versions of reality, the machine malfunctions, leaving behind an unteleported individual, while another version continues elsewhere. To each individual, nothing seems wrong. From their perspective, their consciousness is continuous. But what if they later discover that a failed teleportation event once left an identical version of them behind? How would that affect their understanding of personal identity? Now, take this concept to its extreme. If teleportation is a destruction and reconstruction process, does that mean every teleportation event is a form of death? If an individual uses a teleportation system 10,000 times in their lifetime, have they technically died 10,000 times? Would there be some version of them in another reality that never stepped into the machine at all, believing the entire concept of teleportation is a hoax? Some physicists argue that quantum mechanics does not just describe probability, it describes real, branching realities. The many worlds interpretation suggests that every possible event occurs in some universe. If teleportation has a probability of failure, then there exists a reality where that failure has occurred. But from the perspective of the traveler, they never see the failure. They only experience the realities where they continue to exist. If this is true, teleportation may not be a clean transition from point A to point B. It may be an ongoing quantum gamble, where consciousness always finds itself in a version of reality where it survives the process. A disturbing consequence of this idea is that consciousness could be trapped in an infinitely branching sequence of unlikely survivals. If an individual is about to die in an accident, and there is even a minuscule quantum chance that they survive, then their subjective experience should only follow the realities where they make it through. Everyone else might see them perish, but from their perspective, they always remain alive, no matter how improbable their survival becomes. This paradox extends to teleportation. If teleportation inherently has a failure rate, then there should exist versions of reality where it never works. But from the perspective of the traveler, they will only ever experience the versions where it functions properly. This suggests that even if teleportation has a 1 in a million chance of failing, the person being teleported will always find themselves in the one where they successfully arrive at their destination, no matter how many failures exist elsewhere. But what if teleportation is not just a means of moving from one place to another? What if it is unknowingly splitting reality every time it is used? What if every teleportation event is a new existence, branching off from a previous one, with the user unaware that a version of themselves was just erased in another timeline. Consider the implications for human society. If teleportation creates perfect copies, then in some fraction of cases, those copies will exist simultaneously. Would people begin to fear the process, knowing that some version of them might continue elsewhere? Would individuals refuse to teleport, fearing that each use is a death sentence? Or would society embrace the idea that personal identity is fluid, that people are not fixed entities, but ever-evolving quantum beings, continuously shifting through the multiverse? Then there is the question of memory and continuity. If consciousness is merely a state of information, then in theory, teleportation should preserve it perfectly. But what if memory is tied to something deeper, something quantum that cannot be cloned? If teleportation creates a perfect copy, does that copy have the same awareness, or does it only inherit the structure of past experiences? Could teleportation create an empty shell, a being that looks and acts identical but lacks the subjective continuity of the original? Another complication is the role of probability. If teleportation is inherently probabilistic, then how does an individual perceive which version of themselves is real? If countless versions exist, each experiencing slightly different outcomes, which one represents the true person? Would individuals begin to experience quantum drift, where subtle changes accumulate over multiple teleportation events, altering their thoughts, memories, or even personalities in ways they cannot perceive? There is also the possibility that teleportation could be hacked or manipulated. If the process relies on quantum information transfer, could an external force alter the data mid-teleportation? Could someone arrive at their destination with modified memories, altered behaviors, or an entirely different personality? Could teleportation be weaponized, used to create deceptive clones, or erase individuals from history while leaving a perfect, manipulated version in their place? Even more unsettling is the idea that teleportation could be used to split a single consciousness into multiple independent versions. If a teleportation system were deliberately designed to create multiple copies instead of destroying the original, would each copy continue as an individual consciousness? Would they share experiences for a moment, only to diverge into separate beings with separate lives? And if so, which one would have the right to call themselves the true version? If consciousness is just a pattern, then teleportation should preserve it. But if identity is tied to a deeper, quantum-level phenomenon, then teleportation may be doing something far stranger than simply moving people. It may be fracturing reality, creating countless unnoticed branches where individuals continue to exist, forever unaware of the versions of themselves that ceased to be. Teleportation does not just challenge physics. It challenges the fundamental nature of existence itself. It forces us to question whether we are truly singular beings, or whether we are constantly splitting into infinite possibilities, each unaware of the others. And if teleportation really is tied to quantum immortality, then perhaps stepping into the machine does not end a journey, but begins an infinite one where consciousness never finds an end, only new beginnings. Could teleportation unlock the secrets of time? Teleportation challenges the way we perceive space. It suggests that distance itself might be an illusion, that information does not need to travel in a conventional sense, but can reappear elsewhere without passing through the space in between. But if space is not a fundamental barrier, what about time? Could quantum teleportation reveal something just as unsettling? that time itself is not as rigid as we believe. Teleportation does not transfer objects. It transfers quantum states, the very essence of a system, from one place to another without any physical movement. This is possible because of entanglement, a strange phenomenon where two particles share a connection that allows changes in one to instantaneously affect the other, no matter how far apart they are. These changes do not propagate like normal signals. They happen outside the constraints of space. But what if they also happen outside the constraints of time? Quantum mechanics already suggests that time is not as straightforward as classical physics implies. In the quantum world, the distinction between past, present, and future begins to blur. Some interpretations suggest that entangled particles do not just affect each other across space, but also across time. If true, this would mean that teleportation could reach not only across distances, but also into different points in time. One of the most unsettling experiments related to this idea is known as the delayed choice quantum eraser experiment. This suggests something extraordinary, that quantum events are not fixed until observed, and that their outcomes can be influenced by choices made after they should have already occurred. If teleportation relies on quantum mechanics, could this effect be harnessed? Could teleportation allow us to send information, not just across space, but across time? One possible mechanism for time-related teleportation comes from the nature of entanglement swapping. In current teleportation experiments, entangled particles are used as intermediaries, transferring quantum states between locations. But what happens if entangled particles exist at different points in time, rather than different points in space? Consider this scenario. A scientist entangles two particles and sends one into deep space while keeping the other on Earth. Decades later, the distant particle is used in a teleportation experiment. The entangled connection remains, meaning that when the scientist manipulates the Earth-bound particle, the information still arrives instantly at the distant particle, even though decades have passed. From an outside perspective, it seems as if information has traveled backward in time. The connection between the entangled particles has remained intact, unaffected by the passage of years. But this raises a paradox. Did the information actually travel through time, or was time simply not relevant to the process at all? Some physicists suggest that teleportation, if refined, could exploit this property to create a new kind of communication system, one that is not bound by the linear flow of time. Messages could, in theory, be received before they are sent, disrupting causality as we understand it. If this were possible, it would rewrite our understanding of past and future. There is also the question of black holes and their connection to teleportation. Black holes already challenge conventional ideas about time. Anything that falls into a black hole is seemingly lost forever, yet modern physics suggests that information cannot be destroyed. Some theories propose that black holes do not truly trap information, but instead teleport it to another region of space-time through quantum entanglement. This is where teleportation and time manipulation intersect. If information escaping a black hole is actually teleported elsewhere, then could black holes be natural time machines, moving data not just across space, but across different moments in time? Could quantum teleportation one day allow us to access these deep cosmic connections and retrieve information from the past? Another clue comes from the concept of closed timelike curves, loops in space-time predicted by Einstein's general relativity that theoretically allow objects to return to their own past. If quantum teleportation interacts with these structures, it could provide a way to send quantum states into the past without violating known laws of physics. Unlike traditional time travel concepts that involve physical objects, this would involve only pure quantum information, meaning it could bypass some of the paradoxes associated with classical time travel. But there is a problem. If teleportation can send quantum states backward in time, does that mean we could use it to send messages into the past? Could we warn ourselves of future disasters, altering history before events unfold? Or would the very act of trying to send information backward prevent itself from happening, preserving the consistency of time? Some physicists believe that even if quantum teleportation allows information to move across time, it would never allow for paradoxes. Instead, reality would adjust to ensure that no contradiction occurs. This is known as the self-consistency principle, which suggests that even if teleportation permits time manipulation, it will only allow changes that are already compatible with what has happened. This could mean that if someone successfully sent information into the past, it would only ever be information that was meant to be received, messages that were always part of history, rather than messages that rewrite it. But what if teleportation does not merely send information through time, but creates new timelines altogether? The many worlds interpretation of quantum mechanics suggests that every possible event spawns a new branch of reality. If teleportation allows for time travel, it might not alter the past in a single timeline, but instead generate new alternate timelines where the effects unfold differently. In this case, a person sending a message into the past would never see its effects in their own world. Instead, the altered version of history would exist in a separate branch of reality, accessible only to those within that new timeline. If this is true, teleportation may not allow for time travel in the traditional sense, but instead offer a means of moving between parallel versions of history. Some theories even suggest that our own consciousness is constantly teleporting through time, not physically, but through quantum processes in the brain. Certain interpretations of quantum cognition propose that decision-making involves the brain selecting between superpositions of future possibilities, meaning that every choice we make is a form of navigating through potential futures. If consciousness is somehow linked to quantum teleportation, could this explain intuitive flashes, déjà vu, or even precognition? Could moments where people feel they have glimpsed the future actually be subtle effects of the mind temporarily accessing entangled quantum information from another point in time? There are no definitive answers yet, but teleportation has already revealed that information does not behave the way classical physics suggests. The next step is to determine whether time itself is just another dimension through which quantum states can move freely. If so, teleportation might not just be a tool for moving information. It might be a key to understanding the true nature of time itself. Is the universe itself a teleportation network? Quantum teleportation suggests that information is not bound by space in the way we once believed. If information can be transferred instantaneously between two locations without crossing the space between them, then what does this say about the fundamental nature of the universe? Is space an illusion? Is teleportation not an anomaly, but a glimpse into the hidden architecture of reality itself? The fabric of the universe appears continuous to us, a vast expanse of emptiness punctuated by stars and galaxies. But at the quantum level, space may not be a smooth, uninterrupted expanse. Instead, it may be a web of hidden connections, where distances are not what they seem and information moves through unseen pathways that defy conventional physics. One of the most intriguing ideas in modern physics is that space itself may be an emergent property of quantum entanglement. Instead of being a fundamental feature of reality, space could be a consequence of how information is structured across the universe. If this is true, then teleportation is not just a strange quantum trick. It is a direct interaction with the underlying structure of the cosmos. Consider a vast neural network. Each node is connected not by physical wires, but by information itself. The shortest path between 2 points in such a system is not necessarily the direct, linear route. It is the path of least informational resistance. What if the universe operates in the same way? What if teleportation does not move information across space, but simply reveals that space is already connected in ways we do not yet understand? If this is the case, then our entire concept of distance may be flawed. Teleportation may not require information to travel at all. Instead, it could be an indication that every point in space is already linked to every other point, and that conventional motion is just a limited way of interacting with reality. This idea aligns with a radical but growing view in physics, the holographic principle. This idea aligns with a radical but growing view in physics, the holographic principle. This theory suggests that when we consider the role of black holes are often thought of as cosmic prisons, regions where gravity is so strong that nothing can escape. But modern physics suggests something different. Instead of destroying information, the black hole information paradox has troubled physicists for decades. If information falls into a black hole and is truly lost, if entangled particles can instantly influence each other across vast distances, could black holes be entangled with distant regions of the cosmos in a similar way? If so, then teleportation might not just be about moving quantum states from one place to another. It might be a small-scale version of a process that governs the entire cosmic web, a mechanism that the universe itself has been using since the beginning of time. The implications of this idea are staggering. If teleportation is connected to the fundamental structure of the universe, then it could mean that traveling through space is unnecessary. Instead of physically moving from one point to another, sufficiently advanced civilizations might exploit the universe's hidden teleportation network, jumping instantly across cosmic distances by accessing the underlying entanglement woven into space itself. Could this explain some of the greatest mysteries of astrophysics? Following a hidden structure. Could they be signs of naturally occurring teleportation events, brief moments where information is displaced across the universe? They exist in superpositions, taking on multiple possibilities at once. Some interpretations suggest that instead of these possibilities collapsing into a single outcome, each possibility actually occurs in a separate branch of reality. If teleportation manipulates quantum states, could it also manipulate which version of reality we experience? This would mean that teleportation is not just moving information, it is selecting which timeline to interact with. Instead of traveling through space, teleportation could allow access to alternate versions of history, subtle variations of the universe that exist alongside our own. Even more mysterious is the question of whether consciousness itself is connected to teleportation. If the brain operates through quantum processes, as some researchers believe, then could teleportation occur at a cognitive level? Could moments of sudden insight, precognition, or déjà vu be the result of the mind briefly tapping into the hidden entanglement of the universe? There is also the possibility that teleportation is not something we need to invent at all, but something we need to remember. If teleportation is a fundamental feature of reality, then it is possible that ancient civilizations or even life forms beyond Earth have already understood and harnessed it. Could this explain UAPs, unidentified aerial phenomena, that seem to defy the known laws of physics? Objects observed accelerating instantly, making right-angle turns at impossible speeds, or appearing and disappearing without a trace? If space is truly connected through an invisible teleportation network, then these phenomena may not be traveling through space, but instead rearranging their position within the universe's hidden structure. Teleportation may not be an anomaly. It may be a reminder that we are only beginning to grasp the deeper truths about reality. The universe might not be a vast, empty void where objects move through space. It may be a single, interconnected whole, where distance is nothing more than a perceptual limitation. If this is true, then the future of exploration will not be about building faster spacecraft or traveling across space in the traditional sense. Instead, it will be about learning to access the connections that are already there, about finding the pathways that allow matter, energy, and even consciousness to teleport, not just across galaxies, but across dimensions of existence we have yet to understand. If the universe is a teleportation network, then we are not just travelers moving through space. We are part of a cosmic web that has been connected since the beginning of time. For decades, scientists have treated teleportation as an exotic laboratory experiment, a bizarre demonstration of quantum mechanics with no immediate use outside physics journals. But now, quantum teleportation is stepping out of theory and into the real world. Governments, tech giants, and research institutions are racing to build practical systems that can harness its power, promising to reshape communication, computing, and even our fundamental understanding of the universe itself. The most immediate and revolutionary application lies in quantum communication. Every message sent today, whether a phone call, financial transaction, or classified government document, relies on encryption. Codes protect our data, but codes can be broken. Given enough time, a powerful enough computer can decrypt even the strongest security measures. But quantum teleportation changes this forever. At its core, teleportation provides the ability to transfer quantum states without any physical transmission of particles. If used in communication, it enables quantum key distribution, a method where encryption keys are teleported rather than conventionally sent. Because of the strange properties of quantum mechanics, if an outsider tries to intercept the key, the information collapses, leaving clear evidence of the intrusion. Eavesdropping becomes impossible because the act of listening alters the message itself. China has already begun laying the foundation for a quantum-secure global network. In 2017, Chinese scientists successfully teleported quantum information from Earth to a satellite in orbit, covering over 1,400 kilometers, the longest distance ever achieved. This satellite, named Meteus, has since been used to create secure communications between continents, proving that quantum teleportation is more than just an experiment. It is the blueprint for an entirely new kind of internet, one that cannot be hacked, cannot be forged, and cannot be compromised. But teleportation is not just about security. It is also about speed and efficiency. Current internet infrastructure depends on vast networks of fiber optic cables and wireless signals that are limited by noise, interference, and the fundamental constraints of physics. Quantum networks could bypass these issues entirely, transmitting data with perfect fidelity over long distances, free from the vulnerabilities of traditional communication systems. And yet, teleportation's potential does not stop with information transfer. It also holds the key to unlocking the most powerful computers ever conceived. Modern supercomputers, no matter how advanced, rely on classical bits, units of information that are either 0 or 1. This binary limitation means that even the fastest machines must process information in sequential steps. Quantum computers, however, operate on qubits, quantum bits that exist in multiple states at once. This allows them to solve problems exponentially faster than any classical system. But building large-scale quantum computers comes with a significant challenge. The delicate nature of quantum states makes them highly susceptible to interference, requiring extreme conditions such as near absolute zero temperatures to maintain stability. Worse, for quantum computers to work at their full potential, they must be able to exchange information across vast networks of qubits, something that is nearly impossible using conventional means. This is where teleportation becomes a game changer. Quantum teleportation allows qubits to be transferred between processors without physically moving them. Instead of sending electrical signals through wires, quantum computers can use teleportation to directly transfer computational states from one location to another, creating an interconnected web of quantum processors. This is the foundation of distributed quantum computing, a system in which multiple quantum computers act as one unified machine. Imagine a world where quantum processors are linked across continents, solving problems that classical computers could never hope to tackle. A world where simulations of molecular interactions lead to instant drug discoveries, where materials with unprecedented properties are engineered in virtual quantum environments before ever being built in reality. A world where artificial intelligence operates at unimaginable speeds, optimizing complex logistical networks, financial markets, and even weather prediction with near-perfect accuracy. Quantum teleportation is the missing link that will allow this vision to become reality. But as with any groundbreaking technology, there are challenges. One of the biggest obstacles is quantum decoherence, the phenomenon where quantum states lose their delicate properties due to interactions with the environment. Even the slightest interference from outside forces, thermal vibrations, electromagnetic waves, or cosmic radiation can disrupt entanglement, making teleportation unreliable. To combat this, researchers are developing quantum error correction techniques that detect and correct. Some are working on topological qubits, which are more resistant to decoherence due to their unique mathematical properties, across vast distances, allowing teleportation to work on global scales. There is also the issue of scalability. While individual particles have been successfully teleported, moving beyond single qubit teleportation to entire quantum networks is a massive engineering challenge. Current teleportation systems require extreme precision, often relying on highly controlled laboratory conditions. Transforming these delicate experiments into everyday technology will require innovations in stability, infrastructure, and computational techniques. Despite these hurdles, progress is accelerating. Governments and private companies are investing billions into quantum research, and the European Union are all competing to dominate quantum technology, seeing it as the key to securing economic and military superiority in the coming decades. Yet beyond communication and computing, teleportation's strangest implications lie in physics itself. Some physicists believe that quantum teleportation may hold the key to understanding the fundamental nature of reality. If information can be transferred without any physical medium, does that mean space itself is an illusion? Could teleportation reveal hidden connections between seemingly distant regions of the universe? Some even speculate that teleportation could be a stepping stone toward quantum gravity, the long-sought theory that unifies Einstein's relativity with quantum mechanics. Others wonder if teleportation might one day allow for entirely new forms of transportation, not by moving physical matter, but by reconstructing it elsewhere. While teleporting humans remains in the realm of speculation, the very principles that enable quantum teleportation challenge our notions of identity, location, and even time itself. In a universe where particles can be erased and reborn across vast distances, what does it mean to exist in one place rather than another? Quantum teleportation is not just a technological breakthrough. It is a revelation about the nature of existence. It tells us that information is more fundamental than matter, but a deeply interconnected system, bound together by rules we are only beginning to uncover. What lies ahead is uncertain, but one thing is clear: teleportation is no longer just a theoretical possibility. It is happening now, and its impact will change the world forever. Conclusion: the ultimate question of teleportation. The deeper we venture into the mysteries of teleportation, the more we realize that this phenomenon is not just a technological breakthrough. It is a window into the hidden structure of reality. It forces us to question everything we assume about existence, identity, space, time, and even consciousness itself. But the real question isn't just whether teleportation is possible. The real question is, what does teleportation reveal about the universe we live in? For centuries, walking across a room to sending a spacecraft to another planet follows this basic assumption. But teleportation introduces something entirely different: the idea that information does not need to travel. It can appear somewhere else without crossing the space in between. This suggests that space is not what we think it is. If two entangled particles can influence each other across vast distances instantly, then our classical understanding of separation begins to collapse. Is distance even real? Or is it an illusion created by the limitations of human perception? Teleportation might be more than a scientific achievement. It might be a message encoded in the laws of physics, telling us that our universe is not what it appears to be. But if space is just a construct, what about time? Could teleportation be revealing something even more profound, not just about how things move, but about how events unfold? Our understanding of time has always been based on cause and effect. A moment passes, then another, then another. But teleportation, particularly its interactions with quantum mechanics, suggests that the past and future may not be as distinct as we once believed. The existence of delayed choice experiments, entangled systems that seem to defy temporal order, and the possibility of quantum information moving backward in time all hint at something astonishing. Teleportation may not just defy space, it may rewrite time itself. What if teleportation is not just a way to move things, but I do not yet understand?